if we bring up the name Albert Einstein, most people are familiar with who that is, and they associate his name with E equals mc squared or the theory of relativity. Newton goes with gravity, and people like Alexander Graham Bell go to the telephone. Charles Darwin is the theory of evolution. All of those are people we're familiar with. Today we're going to talk about the atom and people associated with our current understanding of atoms and what they look like and how they function. Because these are not as well known people in most cases. So after today, or with this lesson, I want you to be able to recognize key contributors to the development of the modern atomic theory. You'll be able to correlate their discoveries with the experiments they conducted. You'll be able to draw or recognize diagrams of atoms as we concluded each experiment, as each discovery was made. And then you'll be able to identify the location, mass, and charge of the three subatomic particles found in an atom. This will be kind of our last goal for the day. So let's get started. Atomic theory was developed long ago by a fellow named Democritus. He was a philosopher around the same time as Aristotle. So people know the name Aristotle, very few know the name Democritus. But he had this idea that matter was made of these really small particles, which he called atoms or atomos. And they were small, indestructible, indivisible pieces that piled together and made everything that we know of as today, all the things that we see. And one of the people that argued with his idea was that fellow named Aristotle. And so because of Aristotle's clout and his reputation, people followed Aristotle and didn't give Democritus much thought. And so we don't hear much about him, but he was the first one to say, hey, I think all this stuff is made of small little particles. I don't know what Aristotle's view on things was, but it was obviously different than Democritus. Fast forward something like 2,000 years, 1,500, 2,000 years later, we get this guy named John Dalton, who also proposed that atoms were a small, indivisible sphere of matter. But to go with he had done experiments, and he had these four postulates, four ideas that supported this idea and this claim. So one, he said all substances were made of atoms. And atoms are small particles that cannot be created, divided, or destroyed. So just like Democritus, all things are made of these small little pieces that can't be broken down. He also concluded or decided that atoms of the same element are exactly the same. Atoms of different elements are different, are not the same as the other ones. So iron is the same as iron, oxygen is the same as oxygen. Those two atoms are not alike. His third postulate, in any chemical reaction, atoms are not gained or lost, just rearranged. So chemical reactions happen when atoms are recombined, but I can't make or destroy them. And then when atoms react with others, they do so in specific whole number ratios. So I can't have half an atom I can't have half an oxygen atom and a whole iron atom. I have to have a whole oxygen and a whole iron. Those were his four postulates. And this is in the 1800s. So this is just over 200 years ago we came to this idea. After him was an individual by the name of J.J. Thomson. So we had Dalton's model says atoms are small and indivisible. Thomson discovered that there are smaller parts to an atom. He worked with what are called cathode ray tubes. So TVs, prior to LEDs, prior to LCDs and all these other TVs we have today, they had what were called cathode ray tubes, which shot light particles at a screen, and then using different colors of light, you got your different pictures. He discovered these particles that, because of these cathode ray tubes, and I'll show you his experiment in a second, he discovered what we call electrons today. He found that the atom as a whole is neutral, but they had these electrons which had a negative charge to them. And so he proposed, because they had these negative charges, but the atom itself was neutral, so there had to be a positive somewhere too, he proposed what we call the plum pudding model, which essentially you had this pudding of stuff that was all positive. This has a positive charge. And within that, you have your plums, or think of it like cookie dough ice cream. You have your negative charges built in. This was his model. He won a Nobel Prize for his discovery and his contribution to the atomic theory. This is a cathode ray tube. So we have a positive and negative charge, essentially a battery. Electrons go this way on the negative side, and they shoot electrons from the negative to the positive. So as these particles are shooting, they're going from negative to positive. What he did was he attached a magnet. He would put magnets up here or down here. And he discovered that this beam of light would bend towards the magnet and go across the top. So it wouldn't shoot straight down. It would bend either to or away from the magnet, depending on which magnet you put there. So he discovered that this has a negative charge, concluded this had a negative charge, and so we turned that an electron. This is his model. So again, you have a positive atom itself, and these little negative charges are scattered throughout. Positives and negatives should balance. You should end up with a neutral charge in the end. And so atoms are neutral, but they have these negative particles. This was J.J. Thomson. After him was the guy by the name of Ernest Rutherford. So Rutherford he set up an experiment where he fired what we call alpha particles. And so an alpha particle, which we'll learn about in the next unit, is composed of 2 protons and 2 neutrons. Protons have a positive charge, so he fired positively charged particles at this really thin piece of gold foil. So he took gold and he hammered it, smashed it down so it was a couple atoms thick and very thin, and fired these particles at the gold foil. What he suspected was that all these particles would go straight through to the other side. It would be no big deal, they'd go through, life goes on. What he found was that not only did these particles reflect and hit the sides over here, which he thought, okay, not a big deal, some of them went backwards. So you see these 2 arrows going backwards, so they hit the gold foil and they came backwards. He compared this to firing a bullet at a Kleenex and having it come back at you. That is the magnitude of shock and awe that happened when this experiment took place. So this is kind of a look at what's going on with these particles. So most of the alpha particles go through the gold foil, not a big deal. Some of them, however, collide directly with the nucleus of the atom and come backwards, the centerpiece of the atom, and go backwards. And this is what Rutherford discovered and found, and again was like shooting a bullet at a napkin and having it come back at you, which would be quite alarming. In conclusion, so after his experiment, he came up with 3 more ideas about the atom. So he determined, or he discovered, or claimed that the atom was mostly empty space, because most of the alpha particles went through. Most of the atom's empty space. Nothing there, the alpha particle goes through. However, there's something in an atom, and he discovered the center. He claimed the center, which he termed the nucleus, is very dense and has a positive charge because those positive alpha particles came back at it. And the last one is the nucleus contains nearly all the mass of an atom. So all of the mass is contained, almost all the mass is contained right here in the middle. That is your nucleus. Continuing on, so we had, first was John Dalton, second was J.J. Thomson, and then it was Ernest Rutherford. Now we have Niels Bohr. So we have that the nucleus is in the center, and electrons, the positives are in the center, electrons are on the outside. Bohr suggested that the electrons on the outside travel in specific paths around the atom. They can be found in a path, one path or another path, but they cannot be found in between them. And so think of it like planets in the solar system. Here's the sun. We have Mercury going around this first path, Venus goes on the next one, Earth, Mars, so on and so forth. Now think of it as multiple Venuses, multiple Mercuries, all going in the same path, but that belt. And he concluded there are no electrons found in the gaps. So they can't be found here in the middle. Just like our planets, there's no planet found in between Mercury and Venus. There's nothing found in between Venus and Mars as far as a planetary object. So if you think of it in that sense, that's one way to kind of rationalize it. But electrons can jump. So this electron can go from here to this level, or from this level to the next level, and then back down and vice versa. We'll talk more about this coming up. Again, Bohr won a Nobel Prize, and he also worked with Rutherford. So the guy that came up with the nucleus worked with Niels Bohr, and this was his addition to the atomic theory. After Bohr was a fellow by the name of Erwin Schrödinger. And so, like Bohr said things go in an exact path around the outside. Schrödinger said, yeah, but it's not that easy. We can't know exactly where an electron's going to be. So he concluded or stated that the exact location of an electron cannot be known. And so he developed what we call the electron cloud model. And so electron cloud is a region of space where an electron is likely to be found. So this is a region where there's likely an electron somewhere. Okay? So that was Schrödinger's addition to the atomic theory. And the last man that added to this understanding. So Schrödinger was 1927, just to give you a little timetable. Bohr was in 1911, so we went 16 years in between those two. Rutherford was in 1910, and now we're clear up to Chadwick, who was in 1932. So these are not bing, bing, bing discoveries. They're multiple years in between. Chadwick concluded or discovered that the mass of an atom was roughly double the number of protons in the element, or in the atom. So mass is not adding up as far as protons aren't making up all the mass. There's got to be another particle there. So he discovered this thing we call a neutron in 1932. He worked on what's known as the Manhattan Project, which developed the atomic bomb. Also worked with Rutherford, which means he likely worked with Schrödinger, and won a Nobel Prize as well. So you want to win a Nobel Prize, work with atoms, find something new, there's your prize. All right, so that is the atomic theory. This is, again, so Chadwick didn't really change the model. He just found that there are neutrons in the middle as well as protons. All right, so we've talked about 3 particles. We've talked about a number of people. So make sure you are familiar with the person, the experiment, and their model drawn afterwards. And in doing so, we've talked about different particles associated with atoms. So we have 3 particles. They are protons, neutrons, and electrons. So you should make this table in your notes. And so just to have a quick reference, protons is P with a plus sign, neutrons are N with a 0 sign, electrons are E with a negative sign. So location-wise, protons are found in the nucleus. Neutrons also found in the nucleus. And electrons are found in the electron cloud, or you can write outside nucleus. Either way works. Charge, protons, little plus sign here means charge is positive. Neutrons, 0 means neutral. And E, little dash up there, means negative. And the last piece, protons have a mass of 1 AMU, which means atomic mass unit. Neutrons, also 1 AMU, atomic mass unit. And electrons, 0 AMUs, again, atomic mass unit. It's not actually 0, but electrons are just insignificant compared to the mass of a proton or a neutron. Remember that Rutherford discovered that most of the mass of an atom is in the nucleus, and that is where your protons and neutrons are. They both have a mass we collectively termed 1 AMU. All right. To give you a little perspective, if the nucleus of an atom were the size of a billiard ball, the average electron, so pool ball, billiards means pool, nucleus was the size of a pool ball, the electron is going to be roughly a mile away and very small. And if your electron had the same mass as a penny, the mass of a proton or neutron would be 11 pounds, which is a bowling ball. So think of this. If you put a penny on top of a bowling ball, did you really change the mass? Not significantly. So that's why we say the electron has a mass of 0. It doesn't change the mass of this atom as a whole. All right. For your closure, I would like you to name 2 individuals who contributed to the atomic theory, including their experiment and their atomic model. Make sure you can do this for tomorrow, and then we'll pick back up and continue our discussion on the development of the atomic theory and atoms as we know them today.